One of my favorite experiments in the lab is called evaporation and intermolecular forces of attraction. I have my students do this, collecting a lot of data points very quickly by using technology. I'm going to start today by using 3 different alcohols. The alcohols are sitting here. They are methyl alcohol, methanol, ethyl alcohol, ethanol, and propyl, N-propyl alcohol. Now the setup is simple. I have 3 temperature probes like this one. You'll notice that the temperature probe has a diaper on the end of it. Not really a diaper, it's just a piece of paper towel. And the paper towel has been folded around the tip of the probe, which is where the temperature readings are actually detected. And then secured with a rubber band so that it's going to remain at the tip of the probe. Now, I give 3 probes to my students, and they're simply told to wrap a paper towel around the probe. They're not told how to do it, just to get the job done. And their only instructions are to be sure that whatever they do, that all 3 probes are treated exactly the same. The same amount of paper towel, put at the exact same position, the exact same way. You want to make all 3 identical. So I did all 3 wrappings. Now, to make this interesting, I have 3 different containers here. Each of the containers is one of these alcohols, but I haven't labeled which is which. We're going to do the experiment, look at the data, and then try to determine which alcohol is in each of the vials from the data that we record. The only instructions I then give my students is to take the probes. We're going to dip them into the alcohols just to wet the tip of the probes and have the paper towel soaked. We're going to pull the probes out all at the same time, and then we're going to put the probes down. I don't want my students holding the probes. And wherever we put the probes, all 3 of them, have to be in a similar location, a similar positioning. As soon as that's done, we're going to go to the LabQuest. And Mike has already set up the LabQuest to take data from all 3 probes. It's going to be recording changes in temperature. We'll be able to see this. And we're going to take data for 120 seconds. That's not too very long for an experiment in a chemical lab. So let's point down. And Mike, on the count of 3. 1, 2, 3. Down. They're soaked. Remove. Lay the probes down. All we're going to do is make sure that the probes are off the tabletop, and Mike's going to start the experiment. Okay, now I don't have a good vision to see what's going on the screen, but you should be seeing data points collected how often, Mike?
They are being collected at approximately 2 every second.
2 data points every second. And as these data points are being collected, as the temperatures are being registered at the probes, the LabQuest is going to go ahead and start a graph of the changes in the temperature. You can see that time is on our x-axis, changes in temperature. The temperature readings are going to be along our y-axis. And so the graph is being created as the changes occur.
It appears to me that they're not all cooling off at the same rate.
Well, there's got to be a reason for that, wouldn't you think?
I would think so.
Yeah, we could go ahead and talk about that. Well, in this particular experiment, we're using 3 different alcohols. Now, the difference, let's talk about similarities and differences. They're all alcohols, so they all contain the same functional group, an OH group. And the stem of these alcohols is what varies. Methyl alcohol has a 1-carbon chain. Ethyl alcohol, 2 carbons. Propyl alcohol, 3 carbons. So we're simply lengthening the carbon chain, making the molecule larger. And then at the end of the chain is an OH, hydroxyl group. So, how is this going to affect the intermolecular forces of attraction? Well, all the molecules are going to have a London force. A London dipole interaction will be present in some of the molecules. But the London forces are present in each of these, and yet they vary depending on the size of the molecule. So as we go from the methyl to the ethyl to the propyl, from 1 to 2 to 3 carbons, and the molecules get larger, London forces are going to increase in size. What's going to be similar is that there is an oxygen in each of these molecules in the OH functional group, so we're going to have a dipole moment. There's going to be a dipole-dipole force of attraction, but each of these contain one OH functional group, and so that's going to be consistent from one molecule to the next. The difference is going to be caused by the London forces and by the size. Now, the stronger the forces of attraction, the tighter the molecules are going to be held together, the harder it's going to be for those molecules to evaporate. So, since methanol has the weakest forces of attraction, the smallest London force, it will be held together less tightly. It will evaporate easier. Now, what happens when molecules evaporate? Well, there's lots of molecules in our sample, and not all the molecules have the same amount of energy. The molecules that are going to evaporate will have the highest energy. That means that the molecules with lower energy are left behind. You know, we think about this all the time. When we sweat and we have moisture on our skin, as we sweat and then the sweat evaporates, that helps to cool our bodies. And a lot of women like using an after bath splash. A lot of it contains an alcohol base. Why? Because the alcohols are going to evaporate faster than water, and that gives us a greater cooling effect. Love it after a tennis match in the hot summer days. Okay, so we lose the high energy particles. The lower energy particles remain longer when evaporation is going to occur, and so we see the temperature is going to drop. What do you think, Mike?
It's run and it's completed itself.
All right. The experiment's over now, and we can see that the 3 alcohols did evaporate at different rates. One alcohol, this alcohol has only changed its temperature very slightly. There is a decrease as evaporation has occurred, but it's not a large decrease. And in contrast, this alcohol has really changed temperatures. A lot of particles have evaporated, gone away to leave the cooler particles behind, and a much greater decrease in the temperature of our system. So which would be which? Well, if it's the methanol that has the weaker forces of attraction, then the methanol is going to evaporate faster, and you're going to see...
Tap it. It went to sleep.
You're going to see greater cooling effects. This would be our methanol. In the middle, we would have our ethanol, and then the top graph would be for the propyl alcohol. So, what would I want to do with this? Well, this means that I can now identify which alcohol is in each of the bottles. Okay, so Mike, can you tell me by looking at the screen which one of these was in channel 1?
Channel 1 is the very, very bottom graph.
Okay, this is channel 1. This is our methanol.
That evaporated the most.
Here's our methanol bottle, methyl alcohol. That evaporated the most. And what's in channel 2? That would be our orange one here, channel 2.
Channel 2 is the highest one. That would be the blue with the squared data protection points.
Top graph. Didn't mean to put that line there, Mike. Sorry. Okay. This is our propyl alcohol. I didn't want to put them out in order. I wanted to have the graph to be forced to match up the data that we've graphed with what we have in the vials. And then, of course, our last one, I mixed these up. This is our propyl, and this is our ethyl alcohol, which is the middle graph here. Well, this is a quick way of looking at intermolecular forces and how it can vary within a family of compounds, all alcohols. What I do next is I say to my students, could we make this into a real project? Is there something that you can go out and investigate on your own? What do you know can affect the rate of evaporation? And one of the first things they say would be, well, what if we weren't using alcohols? What if we were using different liquids and from different families? So we might take something like a hexane, which is a straight chain alkane, 6 carbons, it's a liquid. Let's compare a hexane with hexanol, a 6 carbon alcohol. How would their rates of evaporation differ? There are other things that we can investigate. Mike, got an idea?
I know that occasionally my students will ask me about the temperature. What if we tried the probes in different temperatures or looked at the change of evaporation in different temperature settings?
Mm-hmm. How could you do that?
You could put it in a cooler that has some ice off to the side, refrigerator, put it under a heat lamp, check the different temperatures at which we could evaporate things.
See how that would affect your graph. Another thing that you could do, you could check for humidity. I'm a girl from Atlanta, Georgia, and they're always telling me how hot and humid it is in Atlanta. The heat's going to help everything to evaporate, but the humidity doesn't help at all. So how can I test that? Well, what if I had 2 probes and I was going to look at the rate of evaporation, but I put one probe into a baggie where I had a paper towel and very low humidity because of adding some dryerite, something that would help remove the humidity from the air. And in another bag, I would put a paper towel that was soaked in the liquid that I was going to look at the evaporation rates. So I would have a dry environment, I would have a humid environment. I wonder how that would affect my graph. Got another idea?
What would happen if you were to have movement of air across the temperature probes, such as a sling psychrometer where we moved it around to check the humidity?
Yeah. You know, we had all of these laying in a position where they were hanging off the side of the counter. The surface area, the area exposed to the air where the evaporation was going to be occurring, all around the probe. How could you change that? Wind currents, moving it around. That would affect the rate. Would it make a difference if the probe were laying on the table or hanging off the side of the table? It's going to affect the surface area. So there's lots of investigations that students can now pursue on their own. And if the kids get excited about the science, they want to go out and explore. I can't think of a better way to learn and understand science than through your own investigations.